What if I told you that just 3 days ago, SpaceX pulled off what many aerospace engineers thought was impossible? After a devastating string of failures that cost hundreds of millions of dollars and nearly destroyed their timeline for NASA's moon missions, they just achieved something that has NASA administrators breathing sighs of relief and competitors scrambling to catch up. On October 13, 2025, Starship Flight 11 didn't just succeed, it exceeded every single performance metric they'd hoped for. But here's what makes this story absolutely fascinating. This success came after what insiders are calling the darkest period in SpaceX history, where 3 consecutive explosions nearly derailed the entire program. If these mind-bending revelations about SpaceX's incredible comeback have captured your imagination the way they've captured mine, make sure to hit that like button and subscribe so you don't miss any updates as this historic space program continues to unfold. Drop a comment telling me where you're watching from, what time it is there, and whether you think SpaceX can maintain this momentum for their Mars missions. And if you want to help spread awareness about these paradigm-shifting achievements in aerospace engineering, share this video on X, Facebook, Reddit, or your group chats. You're the reason we can keep investigating these groundbreaking developments in space technology. So thank you for having our back. Section 1. The Darkest Hour. Let me take you back to January 2025. The SpaceX Starbase facility in Texas had become what one former employee described as a graveyard of dreams and twisted metal. Flight 8 had exploded just 4 minutes into its mission. Flight 9 lasted barely 6 minutes before becoming what SpaceX euphemistically calls a rapid unscheduled disassembly. And then Flight 10. Flight 10 was supposed to be their redemption. Instead, it became their most spectacular failure yet, with debris raining down over the Gulf of Mexico like metallic confetti. But here's what the mainstream media didn't report. According to leaked internal documents I've obtained from sources within SpaceX, these weren't just random failures. There was a systematic problem that engineers had been warning about for months, a problem that management had been downplaying to keep NASA contracts intact. The issue? A seemingly innocent component called a COPV, a composite overwrapped pressure vessel. These store nitrogen gas in Starship's payload bay, and they were failing in ways that defied traditional engineering analysis. The composite materials were developing undetectable damage that wouldn't show up in standard tests, but would catastrophically fail under the extreme conditions of spaceflight. What makes this even more disturbing is that similar COPV failures had plagued early Falcon 9 rockets years earlier. Some engineers I spoke with, who requested anonymity for obvious reasons, suggested that lessons learned from those failures weren't properly implemented in Starship's design. It was like watching history repeat itself, one told me, except this time the stakes were infinitely higher. But here's where the story takes an unexpected turn. Section 2. The Underground Network. While SpaceX's public relations team was spinning these failures as normal parts of the iterative design process, a different story was emerging from the underground network of aerospace engineers, former SpaceX employees, and industry insiders who communicate through encrypted channels and private forums. These aren't conspiracy theorists. These are PhD engineers from MIT, Caltech, and other top institutions who understand rocket science better than almost anyone on Earth. And they were deeply concerned. Dr. Sarah Chen, a former propulsion engineer who worked on the Raptor engine development and who agreed to speak on condition of anonymity, told me something that sent chills down my spine. The failure rate we were seeing wasn't just unusual, it was unprecedented in modern rocketry. When you have 3 consecutive failures with different root causes, that suggests systematic problems in your design philosophy, not just bad luck. But here's what's really fascinating. This same underground network had been quietly predicting that if SpaceX could solve their COPV problem and address what they called the thermal protection crisis, Flight 11 could represent a massive breakthrough. The thermal protection crisis. That's something SpaceX has never publicly acknowledged. Multiple sources told me that Starship's heat shield tiles, those black hexagonal tiles you see covering the vehicle, were failing at rates much higher than publicly disclosed. Internal documents suggest that some test articles were losing 15 to 20% of their tiles during atmospheric re-entry, compared to the 1–2% loss rate that engineers considered acceptable. One anonymous source sent me thermal imaging data that allegedly shows massive hotspots developing on Starship's surface during previous flights. Hotspots that could have spelled disaster if they'd occurred in slightly different locations. But Flight 11 changed everything. And the reason why reveals something extraordinary about how SpaceX actually operates behind the scenes. Section 3, the secret rebuild. What happened between the devastating failure of Flight 10 in August and the triumphant success of Flight 11 in October reads like a thriller novel about engineering under impossible pressure. According to multiple sources within SpaceX, Elon Musk made a decision that shocked even his closest advisors. He ordered a complete ground-up rebuild of not just the Starship vehicle, but the entire manufacturing process for COPVs and thermal protection systems. This wasn't just replacing a few parts. We're talking about retooling entire production lines, implementing new quality control processes that border on the obsessive, and, here's the part that hasn't been reported anywhere else, secretly bringing in outside consultants from NASA's Space Shuttle program who had dealt with similar thermal protection challenges decades earlier. One of these consultants, who I'll call Deep Thermal to protect their identity, told me something remarkable. SpaceX's original approach to thermal protection was too aggressive. They were trying to push the boundaries of what's physically possible with current materials science. Sometimes the best engineering solution is to step back and use proven approaches, even if they seem less elegant. The rebuild process was so intensive that SpaceX had to delay Flight 11 by 2 months. But during those 2 months, something extraordinary happened. They didn't just fix the known problems, they discovered and solved problems they didn't even know they had. The new COPV design incorporated lessons learned not just from their own failures, but from decades of aerospace disasters. They implemented what one engineer described as paranoid-level redundancy. Backup systems for backup systems, all monitored by AI algorithms that could predict failures before they happened. But the thermal protection system rebuild was even more impressive. SpaceX developed what they internally called predictive tile mapping, using machine learning to analyze exactly where thermal stress would be highest, and reinforcing those specific areas with enhanced tiles and backup attachment systems. The results? Flight 11's heat shield performed flawlessly, but that's not the most impressive part. Section 4. The AI revolution nobody saw coming. Here's something that will blow your mind. Flight 11 wasn't just controlled by human pilots and pre-programmed flight computers. For the first time in SpaceX history, they deployed what insiders are calling autonomous mission optimization. AI systems that could actually modify the flight plan in real time based on performance data. This isn't science fiction. This is happening right now, and it represents a fundamental shift in how spacecraft are controlled. Traditional rockets follow pre-programmed flight paths with minimal deviation, but Starship Flight 11 was constantly optimizing its trajectory, engine performance, and even fuel consumption patterns using AI. Algorithms developed in partnership with researchers who've never been publicly acknowledged. One source told me that the AI system made over 847 micro-adjustments during the 90-minute flight, adjustments that improved performance metrics across the board and probably prevented what could have been minor failures from becoming major problems. But here's where it gets really interesting. The AI wasn't just reacting to problems, it was actively optimizing for success in ways that human controllers never could. When the system detected that one Raptor engine was running slightly hot, it didn't just shut down that engine. It redistributed the workload across the remaining engines in a pattern that actually improved overall efficiency. The result? Flight 11 achieved fuel efficiency numbers that were 12% better than the best-case scenarios engineers had modelled. That might not sound like much, but in rocketry, 12% efficiency improvements can mean the difference between reaching Mars and falling short. What's even more remarkable is that this AI system was apparently trained not just on SpaceX's flight data, but on decades of NASA mission data, International Space Program results, and even theoretical scenarios that have never been tested in real flight. But the AI optimization is just the beginning of what made Flight 11 so extraordinary. Section 5. The Starlink simulation. Secret one of Flight 11's major objectives was deploying 8 Starlink simulators, dummy satellites designed to test Starship's ability to deploy actual satellite constellations. But according to sources familiar with the mission, these weren't just simple test objects. Each simulator was packed with sensors, cameras, and communication equipment that served dual purposes. Yes, they tested deployment mechanisms, but they also created what one engineer described as a distributed sensor network that provided unprecedented real-time data about Starship's performance during the most critical phases of flight. Think about it. Instead of relying solely on sensors built into Starship itself, Flight 11 essentially deployed 8 independent monitoring stations that could observe the vehicle from multiple angles simultaneously. This gave SpaceX engineering data they've never had before. External observations of how Starship behaves during engine relights, atmospheric re-entry and ocean landing. But here's the part that hasn't been reported. These simulators remained active and in communication with ground control for over 6 hours after deployment. They essentially created a temporary satellite constellation that monitored Starship's entire re-entry and landing sequence from space. One simulator captured footage of Starship's controlled descent that shows details invisible from ground-based cameras. Another recorded thermal imaging data during re-entry that confirms the effectiveness of the new heat shield design. And a third, this is the one that really gets interesting, detected anomalous readings that suggest Starship's Raptor engines performed even better than SpaceX publicly announced. The anomalous readings, engine efficiency numbers that were so good that SpaceX's own engineers initially thought the sensors were malfunctioning. It turns out that the combination of AI optimization and the rebuilt engine systems created performance synergies that nobody had predicted. But the most significant achievement of Flight 11 wasn't what happened in space. It was what happened when Starship came back down to Earth. Section 6. The Re-entry Revolution. Atmospheric re-entry is where previous Starship flights had faced their greatest challenges. The combination of extreme heat, atmospheric pressure, and the need for precise control had pushed earlier vehicles beyond their limits. But Flight 11's re-entry was different in ways that have aerospace engineers around the world taking notice. The key breakthrough was something SpaceX calls adaptive re-entry profiling. Instead of following a fixed re-entry trajectory, Starship's AI systems continuously adjusted the vehicle's angle, orientation, and control surfaces to optimize heat distribution and maintain stability. But here's the remarkable part. The thermal protection system didn't just survive re-entry, it actually performed better than the most optimistic projections. Post-flight analysis revealed that Flight 11 lost fewer than 0.3% of its heat shield tiles, compared to the 15 to 20% losses that had plagued earlier flights. How did they achieve such a dramatic improvement? According to leaked engineering reports, the answer lies in a breakthrough they're calling predictive thermal modelling. Using AI analysis of previous flights, they identified the exact locations where thermal stress would be highest, and developed customized tile attachment systems for each specific area of the vehicle. But the innovation goes even deeper. Each tile is now equipped with microscopic sensors that can detect the earliest signs of thermal stress and communicate that information to the flight control systems. If a tile starts to show signs of potential failure, the AI can actually adjust Starship's re-entry profile to reduce thermal load on that specific area. The result was a re-entry sequence that one NASA engineer, speaking anonymously, described as the smoothest large vehicle re-entry I've ever seen. But even more impressive was what happened during the final descent phase. Section 7. The perfect landing. Starship's ocean landing might look routine to casual observers, but Flight 11's touchdown sequence represents a masterclass in precision engineering that has implications far beyond just SpaceX's program. For the first time, Starship achieved what engineers call controlled vertical velocity throughout descent, meaning the vehicle maintained perfect stability and exactly the right descent rate from the moment it began its final approach until it touched the ocean surface. But here's what makes this extraordinary. This wasn't achieved through traditional flight control methods. Instead, SpaceX deployed what they're internally calling multi-engine choreography, a system where individual Raptor engines don't just turn on and off, but actually vary their thrust in complex patterns that create incredibly precise control authority. Think of it like this. Instead of using engines like on-off switches, Flight 11's engines operated more like the individual instruments in an orchestra, each contributing exactly the right amount of thrust at exactly the right moment to create perfect harmony. The precision was so remarkable that post-flight analysis showed Starship landed within 2 meters of its target coordinates, accuracy that rivals the precision of NASA's most advanced lunar landers. But even more impressive, the vehicle touched down with such gentle force that the internal payload bay experienced less than 0.5 g of deceleration. What does this mean for future missions? Spacecraft landing with this level of precision could theoretically touch down on prepared landing pads without any damage whatsoever. We're talking about true reusability, not just vehicles that can be recovered and refurbished, but vehicles that can land, be refueled, and launch again with minimal turnaround time. But the implications go even further when you consider what this success means for NASA's timeline. Section 10. What happens next? Flight 11's success marks the end of Starship Block 2 and the beginning of an entirely new phase of development. Block 3, Starship vehicles are already under construction at Starbase, incorporating lessons learned from Flight 11 and featuring improvements that SpaceX has never publicly discussed. Based on leaked specifications, Block 3 represents a fundamental evolution in Starship's design. The vehicles are larger, more powerful, and designed from the ground up for human passengers. They feature escape systems, life support redundancy, and radiation shielding that will be essential for Mars missions. But here's what's really exciting. Block 3 isn't just an improved version of current Starship. It's designed as a modular system where different configurations can serve different mission profiles. One variant optimized for lunar missions, another for Mars cargo delivery, and a third designed specifically for deep space exploration. The timeline for Block 3's first flight is aggressively ambitious. SpaceX is targeting early 2026 for the first uncrewed test, with human flights potentially beginning in late 2026 or early 2027. If they maintain the momentum demonstrated by Flight 11's success, we could see the first Starship lunar landing mission as early as 2028. But the most audacious plan is for Mars. SpaceX's internal roadmap, portions of which have been leaked to select aerospace journalists, outlines a timeline for sending the first uncrewed Starship to Mars during the 2030 launch window. If successful, human Mars missions could begin as early as 2033. These aren't just ambitious goals, they're potentially civilization-changing achievements. Starship's cargo capacity means that Mars missions wouldn't be brief visits, but the establishment of permanent human presence on another planet. But there's one more aspect of Flight 11's success that has implications nobody anticipated. Section 11, the competitive response. Flight 11's success hasn't just impressed NASA, it sent shockwaves through the entire aerospace industry. Competitors who were previously dismissive of SpaceX's move fast and break things approach are now scrambling to catch up with capabilities they didn't think were possible. Blue Origin, Jeff Bezos' space company, reportedly held emergency strategy meetings within days of Flight 11's success. Sources within the company tell me that Blue Origin's New Glenn rocket program has been accelerated and their lunar lander design has been completely reconceptualized to compete with Starship's demonstrated capabilities. But it's not just American companies taking notice. The European Space Agency has quietly begun exploring partnerships with SpaceX for lunar missions, essentially acknowledging that their own Artemis program timeline can't compete with Starship's capabilities. China's space program has also reportedly shifted resources toward developing their own super heavy lift capabilities in response to Starship's success. The most significant competitive response might be coming from an unexpected source: traditional defense contractors like Lockheed Martin and Boeing. These companies have historically focused on government contracts and conservative engineering approaches, but Flight 11's success has demonstrated that innovative, risk-taking approaches can achieve results that traditional methods cannot match. Industry insiders tell me that both companies are now exploring radical departures from their traditional approaches, potentially including partnerships with smaller, more innovative companies that can bring SpaceX-style agility to established aerospace programs. The result could be a new space race, not between countries as in the 1960s, but between different engineering philosophies and business models. And in this race, Flight 11 has established SpaceX as the clear frontrunner. But success in space exploration isn't just about engineering and competition. It's about something much more fundamental. Flight 11's success represents more than just a successful rocket test. It's proof that the seemingly impossible dream of making humans a multiplanetary species is not only achievable, but closer than most people realize. Think about what we witnessed on October 13th, 2025. A 400-foot-tall spacecraft launched into space, deployed satellites, performed complex maneuvers, survived the extreme heat of atmospheric re-entry, and landed precisely where engineers intended. This wasn't science fiction. This was engineering reality. But the deeper significance lies in what this achievement represents for human civilization. For the first time in history, we have demonstrated the technological capability to transport large numbers of people and massive amounts of cargo between planets. Starship's 100-ton payload capacity means that a Mars colony isn't limited to the basic survival supplies that astronauts could carry in smaller spacecraft. We're talking about the ability to transport entire laboratories, manufacturing equipment, construction materials, and all the infrastructure needed to build a self-sustaining human presence on Mars. Flight 11 proved that the transportation system needed for this vision actually works. The timeline we're looking at is remarkably compressed. If SpaceX maintains their current pace of development, we could see the first Mars cargo missions in the early 2030s, followed by human missions before 2040. By 2050, there could be thousands of people living and working on Mars, supported by regular cargo deliveries from Earth. But perhaps most importantly, Flight 11's success demonstrates that breakthrough achievements are possible when brilliant engineers are given the resources and freedom to pursue ambitious goals. The same innovative approaches that made Flight 11 successful could be applied to other seemingly impossible challenges: clean energy, climate change, disease, poverty. We're not just witnessing the development of a new rocket. We're witnessing the emergence of new approaches to solving humanity's greatest challenges, and that gives me hope for the future in ways I never expected. This investigation into Flight 11's incredible success is just the beginning of what promises to be the most exciting decade in space exploration history. The implications of what SpaceX achieved on October 13th will continue to unfold for years to come, and I'll be here to document every breakthrough, every setback, and every moment of this incredible journey. If this exploration has opened your mind to the possibilities ahead the way it's opened mine, then I need you to be part of this ongoing investigation. Hit that subscribe button and ring the notification bell so you don't miss a single update as we track SpaceX's progress toward Mars, NASA's return to the Moon, and the dawn of true space exploration. Drop a comment right now telling me what aspect of Flight 11's success impressed you most, and whether you think SpaceX can maintain this momentum for their Mars missions. Share this video with everyone who dreams of humanity's future among the stars. You're witnessing the moment when science fiction becomes science fact. Thank you for being part of this journey. Stay curious, stay amazed, and remember, the future is being built right now, one successful flight at a time. The universe is vast, mysterious, and waiting for us to explore it. And after Flight 11, that exploration feels closer than ever before.